Hi everybody. Today we will talk about the divisibility, irreducible elements, and prime elements in a ring. So this is lecture 12. So this title we wrote last time. Okay, let's start. So let's suppose that R is an integral domain. R is an integral domain. So today, let's change color. Just color, good. Suppose R is an integral domain. So here is a definition. Here's a definition. If A and B, if A, B are two elements of R, we say that B is a multiple of A. Of A, or B, A divides B. Divides B, and we write it like that. A divides B. If there is an element C in R, there is an element C in R, such that B is equal to A times C. Just like in the for the integer case. So remember in the for natural numbers, or just talk about integers. So for example, let's say 3 divides 6, because we can write 6 as 3 times 2, 2 times 3. So that so if we can write B as a product of A times C, then we say that A divides B, and also C divides B, of course, in that case. And we write, so here's another definition. If A divides B and B divides A, then we say that A and B are associates. And we write A is A tilde B like that. So let example. The first example. So if X is associated to B 0, then it means X is 0 times C for some C in R, and also backward. And this is also true if and only if and also and 0 is equal to X times C. So this implies that X is equal to 0. X is equal to 0, so that if X is equal to 0, of course, it is associated to itself. So the only element associated to 0 is 0. So that the only that associates that is on elements, the only element, let's say, the only element that is associated to 0 is 0. And second, suppose x is associated to 1, then x divides 1 and 1 divides x. So since for some, so that so since x divides 1, so that we can write 1x times y for some y in R. So that means x is a unit. So if x is a unit, then x is, so if x is associated to 1, then x is a unit. And if also x is unit, then we can write x times y is equal to 1 for some y, so that x is x divides 1. And this 1 divides x is always true. Always true. So therefore, so 1 divides everything. So therefore, x is associated to 1. So i.e. we have that x is associated to 1 if associated to 1 if and only if x is a unit. Okay, so here is a proposition. And so this is not for only for 1, and this for any two elements. X a is associated to b if and only if a is equal to b times u for some unit u in R. Or we write it like this: little u is inside this group. So here's a proof. Proof of this proposition. So this way, suppose that A is associated to B. Suppose this implies that A divides B and B divides A. So that means B is equal to A times C, and A is equal to B times, since A divides B, B is equal to some A times C, and since B divides A, then A is equal to B times D for some element D. So therefore A is equal to B times D, and that is A times, instead replace this by AC, ACD. If A is not 0, so by the way, if A is equal to 0, we write, of course, A is as 0 times unit, a unit. If A is not 0, so by canceling A's from this equality, we get 1 is equal to A times C times D. So therefore, C is unit, C or U, so that A is equal to B times C. Okay, so that where C is unit, as claimed. And conversely, suppose that A is equal to B times U, where U is a unit in R. then since b times u is equal to a is equal to b times u, it implies that b divides a. And also we can write b is equal to a times u inverse, so that a is a factor of b, so that a divides b. So therefore, a is associated to b. A is associated to b. So that proves, that finishes the proof of the proposition. Okay. So here's an exercise. This shows that this is an equivalence relation. On R. And of course, the equivalence class of 0 is just 0, and the equivalence class of 1 is the units, namely UR, as we showed above. Here's a definition. Suppose that B is not unit. So think of integers. In the integers, 2 is associated to -2, or 5 is associated to -5, etc. Those are the only elements associated. And suppose that B is not unit, so that 5, for example, in integers, and if the only divisors of B are units, and its associates, then B is called irreducible. So of course, given an element, an example, given an element B in R, so we can write, and if U is a unit, we can write B is equal to U times U inverse times B, so that U divides B. So any unit divides B, and also if B is associated to C, then B is C times U. Also, C also divides B. So that's clear. So that here, if we have a unit, it divides B, and if we have associate of B, then it also divides B. And if there is no other, this definition says if there is no other divisors, then B is irreducible. So, for example, if we take R to be integers, then irreducible elements are these numbers plus minus P, such that P is prime numbers. These are irreducibles. Is not unit. Also, we can also include 0. 0 is not unit. So according to this definition, 0. Oops, sorry. Only prime numbers. Right. irreducible. Why do I write irreducible like that? Okay, next. So let R and S, oops, not that one, sorry. So therefore, I B in R, which is non-unit element, is irreducible if and only if A divides B implies, right explicitly, implies that A is a unit or A is associated to B. So here's a definition, one more definition. Suppose that 0, so P is an element in non-zero element in R, and P is not a unit. So if P divides A times B implies that P divides A or P divides B for all AB, then we say that P is a prime number. P is prime in R, just like integers in the integers. Remember? Yeah. Okay, here's an example. Again, we'll take R to be the first example. R to be integers. In this case, the units are only plus or minus 1. So if we write 2 is equal to A times B, then A is either plus or minus 2, or A is plus or minus 1. So that so therefore, so if it is 2, it is associated 2, and then B is 1 or minus 1. And if A is 2, then B is unit. If A is minus 2, then B is minus 1 unit. If A is plus or minus 1, then it is unit. So therefore, 2 is irreducible in Z. So we cannot write 2 as a product of 2 non-unit elements. And if you look at the second example, if you take, also not second example, sorry, in this example again, for example, 6 is 2 times 3, and also these 2 and 3 are not units in the integers. So therefore, 6 is not irreducible. So prime numbers in the integers, non-prime numbers are reducible. It's not irreducible. Not irreducible means it is reducible. And also, prime numbers in Z are prime in the above sense. So these are the prime numbers that we know from the number theory, 2, 3, 5, etc. They are prime in the above sense. So this is in general. Let's see. So here's a proposition. If P is a Remember, we are working on integral domain. R is an integral domain. So if P in R is prime, then it is irreducible. Is irreducible. So prime numbers are always irreducible in any ring. So here is proof. Suppose that P, we can write P as A times B. P is a non-zero number, of course. Suppose we write like that. And we need to show that either A is a unit or B is a unit. So that P divides A times B. And since P is prime, by assumption, prime, P divides A or P divides B. If P divides A, then A is equal to P times X for some X, so that in this case, A is equal to Px, and P is A times Bx, so that since P is A is not zero, so A is not zero, B is not zero, of course. So from here, if we cancel A's, we get B times X is equal to 1, so therefore B is unit. B is unit, so that A is associated of P. And if P divides B, then B is equal to P times Y for some Y, so that B is equal to P times Y. So replace this P by A times B, A times BY. So when we cancel these B's, because B is not zero, we can cancel B's from here. This is B. A times Y is 1, so that A is unit. So that therefore P is irreducible. Oops. P is irreducible. Okay. So if P is unit, of course, here we may say that A is associated to P, if you like. So here, this proposition says, remember, if P is prime number, then it is irreducible. Now the question, how about, is every irreducible number is prime? How about the converse? Namely, is every irreducible element is prime? And we will see that this is not the case. How many minutes? I forgot the time. Is it written somewhere? No. Okay. Let's. Okay. Let me finish here because this. I will give an example where that this is not true. This is not true. The converse of about proposition, right? We have proposition. We have this proposition. Converse of about proposition is not true. Namely, i.e., there are integral domains in which not every irreducible is prime. I have an example. I will write this example, but it is rather long, so I will quit this video here, and I will start with the next video with this lecture, with this example.